questions on what we have done so far? So I have shared it. Is it visible?
Yes, sir.
Okay. So did I start recording? Okay, I have started recording. So we have come to the last part of everything is done. Now I will not recap how these things were fit together. I mean, we took the logarithm of L functions and stuff, somewhat like that. So the point is the last step is showing that the L functions do not vanish at 1. For the trivial one doesn't vanish anyway. It in fact blows up as you approach 1. But the non-trivial characters, they don't blow up. I mean, they don't vanish. They don't blow up anyway. They extend all the way to. Okay, there is a little bit of noise. I'll. Kaushik,
Look,
sorry, I paid you. Yeah. Yeah. So so we have to show this non-trivial L functions. But I think people can unmute themselves if they can ask questions, right? Okay. So the L chi of 1 not equal to 0 for non-trivial characters. This is the only point that we need to show. And just to very quickly recap, you may remember that this comes from the following fact that L chi of s was written as e to the log of this. So essentially the exponent has this dominating term chi p over p to the s. And we wanted this to not blow up. The trivial one will, for the trivial character, it blows up. For the others, it should not blow up. That's how we came to this. And now L chi of s is basically e to the this. The rest you can ignore. So whether this blows up or not is equivalent to whether this goes to infinity or 0. But this never goes to infinity. So the only thing is whether it can go to 0 as s goes to 1. So this is the last remaining step to show that L functions don't vanish at 1. And we in fact mentioned this following lemma. We mentioned two lemmas. One is that the product of the L functions has this form. As a corollary of it, the product is actually greater than equal to 1 for all s bigger than 1. Okay, I will probably write this lemma again. So one form was this. I will recap the things when I prove this lemma. But and then so this is product over all primes co-prime to d. D is our basic base. So 1 over 1 minus p to the s f of p g of p. F of p g of p are defined below. I will come back to that, but whatever it is, this number is reciprocal of something less than 1, so it's greater than equal to 1. So this whole product is greater than equal to 1 for all s bigger than 1. So that is the key point, because of which, and here this is the part I will recap. So this I have not proved yet. Okay, either this lemma or this lemma. So I will prove this lemma from which the other one will follow. But how is it being used? This I'll recap. So the trivial character behaves like, I made a mistake here. So this is not exactly correct. So let me erase and write it properly. So this is not exactly correct. So the trivial character, you may recall, is not exactly zeta function, but zeta function with an extra factor. Right? Okay, where did the pen go? Yeah. So the zeta, so L chi naught of s is the product over p that divide d of 1 minus 1 over p to the s times zeta function. Now the zeta function as s goes to 1 has the following behavior. So we get that this is product over p that divides d. This is a harmless thing as s approaches 1 times the zeta function behaves like 1 over s minus 1 plus what I had called zeta tilde of s, where this one is continuous on 0 infinity. Okay, so we showed that zeta s has this explosion at 1, but if you subtract that off, you get something that extends all the way to 0 as a continuous function. Therefore, L chi naught of s is like this. So in any case, as s approaches 1, this blows up like 1 over s minus 1, or a constant over s minus 1. The constant being product 1 minus 1 over p, where p divides d. That's a finite number of prime numbers. So that small mistake was there, so I corrected it now. And now what about the other things in the product? So the other things are there in the product. So this one blows up. So the others, this product has to be greater than equal to 1. So if any of them vanishes, if L chi of S goes to 0, actually I have now put it as exercise in the notes, which I'll upload after class. These L chi's are actually smooth all the way up to 0. Therefore, near 1, they would behave not simply vanishing at 0, but they will vanish linearly, like S minus 1 times the derivative, which can be even 0, so it can be a higher level vanishing also. That's possible a priori. But the point is, so it will vanish at least like a linear term. Now, if two of the L chi's vanish, then there will be two S minus 1 factors here in this product and one over S minus 1 factor. So the whole thing will cancel and you will get that the product will go to 0 as S goes to 1. Okay, so if two of the L chi's are such that L chi 1 is 0, L chi 2 is 0, then the product will actually approach 0 as S goes to 0, because you will see you take this is harmless, 1 over S minus 1 plus zeta t. This is nice. So you're multiplying by S minus 1 square times some regular function. So everything will vanish. So for the same reason, L chi also cannot have a second degree vanishing. It cannot be like S minus 1 square times something for the same reason. So this shows that two characters cannot vanish or one character cannot vanish to a second order. Now, but that doesn't quite prove that one of them cannot vanish. Okay, but it does almost, because when one of them vanishes, then the conjugate character also has vanishing, because L chi bar is just L chi conjugate. Okay, so the conjugate character will have the its L function is the conjugate. So if one of them vanishes, the other vanishes. However, these two need not be distinct. That's the only issue. So if you have a really complex character, then there will be two things vanishing and that rules out. So what we have left with is that there could be a real character, that is chi equal to chi bar and L chi 1 equal to 0, and only one of such things, one such thing. Okay, so that possibility is still there. So that we have to worry about. So there are two things to prove. So what remains to prove is this lemma. So this lemma, and second is to worry about the real characters. Okay, so any questions so far? This is what I will prove in the rest of the class.
Yeah, so I mean, just to so the fact that in general chi are complex valued, so L chi is also complex valued, but the argument that you pointed out, chi and chi bar give the same. I mean, they are
Yes.
conjugate. That's why it's real, right? Because otherwise it's not even clear in the beginning that L chi bigger than 1.
Yeah.
A priori it is complex valued, but because
Yeah.
the conjugate pairs are
There,
conjugate L chi, that's why it's yeah.
that is, but this formula also shows that it is in fact actually real valued and positive actually. So we'll prove this without actually directly using that there are conjugate pairs. Of course, it's implicit in it, you will see in the proof. But that's the reason why this is real valued and positive. Yes. A priori, this product could have been complex valued, but it's real valued. Yeah, that's right. So this leaves two things: proving this lemma and proving the non-vanishing for real characters. Okay. So I will do that. So maybe the lemma I will prove here itself, since I have written this. So let me prove the lemma here itself. What happened here? What the hell was this? Okay. So this all I explained. So maybe I just erase all this. This is not needed anymore. Let me have the statement of the lemma in front of me. There must be a better way to erase, but okay, so we will prove this and this will prove the other lemma also. Afterwards, we'll go to the non-vanishing of real characters. Okay, so proof of the lemma. So why is this product of L functions equal to this? So we already know the product formula for L functions, right? So we know that L chi of S is product over primes 1 minus chi of P over P to the S inverse. Okay, you can note that it's anyway only the so you might as well take it over P that are co-prime to D, because for other P chi of P is 0, so this product is 1. So you can also write it over, this is also over P comma D equal to 1. There is no harm in writing that because the other factors are 1 anyway. So now when we take this product over all characters, so we will get product over characters, product over P, and this is a finite number of them. So we are taking product over ZD star hat. So we'll interchange and write for each P, we'll take the product over chi of this quantity, 1 minus chi of P over P to the S inverse. Okay, we'll take the product over all characters. So this is the thing that we need to analyze. So let's consider product 1 minus chi of P. So fix P and consider product chi of P. I mean, all this is not relevant. So let's put just a variable here, Z. Okay. So just look at this product over chi. What is that? So this is what we want to figure out. This will turn out to be this thing. Okay, so this will turn out to be this.
There is a inverse, no? Inverse.
But I will come to that later. So this product will turn out to be what is here in the denominator. Okay, so claim is, so this is the claim, is that it is 1 minus Z to the F of P whole to the power of G of P. So let's recap. F of P is the order of P in ZD star. That is the smallest power such that it is congruent to 1 mod D. And right, I mean, so smallest power of P, which is congruent to 1 mod D. Of course, it's only for coprime P, P coprime to D. So fix P coprime to D. That's the only thing that matters. So f of P, there will be an f of P. There is a finite order, so there will be such a thing. And G of P is the size of the group divided by the order. So it is the size of the quotient, if you want. We won't use any of that, but so this is what we have to get. So this is going to be the claim, and from this claim, this will follow, right? So this will imply this, because your Z is going to be 1 by P to the S. So you will get 1 minus 1 by P to the S f of P whole raised to the G of P, and there is an inverse of the whole. So there is a whole inverse. Okay, so this implies this, and from there you get that. Okay, so this is the only thing to prove this claim. Now it is sort of more or less clear. So what is this? This reminds you of something, right? So if you take the product over all the roots of unity, so 1 minus Z times e to the 2 pi I k over some number, let us say 2 pi I k over some number q. Product k equals 0 to q minus 1. So these are all the roots of qth roots of 1. So this is just 1 minus Z to the q. Right? I mean, it's just the polynomial. So what is the, I mean, if you want, you transfer it as, you pull out a Z to the q out and write it as 1 minus Z minus the you can write like that. Now you see this is just the factorization of the polynomial which has roots at the roots of 1, which is actually 1 by z to the q minus 1. So when you multiply, you will just get 1 minus z to the q. Okay, so that's what it is. So this is very reminiscent of that, and in fact, chi of p is going to be a root of unity. The only thing we have to realize is that which roots of unity, it has to be an fpth root of unity. So now chi of p is an f of pth root of 1, because chi of p to the power f of p is actually chi of p to the f of p, which is chi of 1, which is 1. Okay, p to the f of p is congruent to 1 mod p, 1 mod d, therefore this is 1. So chi of p has to be a pth root of unity. So there are the following fpth roots of unity. Okay, I have written something. So let's say these are the fpth roots of unity, 1 and up to, so let's say w1, w2 up to w f of p. These are the roots of unity. So now suppose if chi of p is some w, let's say w1, then chi square is also a character, by the way. Okay, chi square will map fp to what? It will map p to w2. W2 is w1 square, by the way. Yeah, I could have written it like that. I mean, sorry, let me do it properly. So this is, so let's say this is w, this is 1, which is w to the f of p, which is also 1, w square, w cube, and so on up to w to the f of p minus 1. So now let's chi p be some particular, let's say w. Okay, how many of the chi p has to be one of these? How many times, how many characters are there such that chi p is equal to a particular one? Let me just take w. I could take some general power, but it's the same idea. So suppose chi p is w. What you notice is chi square is another character which maps to w square. Chi cube maps p to w cube, and so on. And chi to the f of p maps it to w to the p, right? So in other words, you can group the characters so that for every character, for every chi that maps p to w, there is one character that maps to w square, another one that maps it to w cube, and so on. So all these are taken an equal number of times. Okay, like this.
So chi of p to fp is 1, right? It's not w power p.
Yeah, which is 1. Sorry, w power f of p. Sorry. Yeah, you're right. It is not w power p, it is w power f of p, which is 1. Which is 1. So all these are taken equally. That's the point, actually. Okay, so all these are taken equally, and that's the point. So right. Okay. So is that okay? So all fpth roots of 1 are taken equal number of times. Why? Chi of p, as chi varies over z star hat. As the characters vary, all these are equally taken. So what that means is that how many times is, so each is taken. So there are f of p of them, and how many, the number of characters is the same as the size of the group, which is phi of d. Okay, so I was maybe denoting phi of d. So each is taken g of p times. Okay, each of these f of p roots is taken g of p times. So from that, this is clear. The claim follows. So in this product, chi of p is w, w square, etc. G of p many times. Each w will come g of p times, w square comes g of p times, and so on. So it is really this product raised to the power g of p with q equal to f of p. And so you get this. Is this okay? So this is how you get this, and from here immediately this follows, and from here this one is clear, right? That it is greater than equal to 1 is clear. Okay, any questions or comments on this? Okay, if not, let me proceed. So what remains? So this lemma is also established. So we have established this as well as this. As I mentioned, there are two different approaches. One is in JP Sir's book, he takes this lemma and takes an approach. It uses a little bit of complex analysis, very little. The other approach is to just use this weaker lemma, but then the only real analysis, but it's a longer analysis. And we have done kind of half of it. The complex characters are taken care of. We have to take care of the real characters. So let me complete that proof. And if there is still time, I'll tell you how in GP Sir's book he does that using a little bit complex analysis. So which everyone may not know. That's why I'll do the real one first. So non-vanishing of, actually, I should say here, L functions for real chi, for real chi. Okay, so this is the only remaining thing, right? You agree to that. So let chi be a real character of ZD star. So that is, so chi maps actually, chi maps, we have extended it to natural numbers, right? So it maps it to -1, 0, and 1. So ZD star itself would get mapped to -1 and 1. It has to map to the circle, but those numbers which are not co-prime to D, so these are chi of n, if n is not co-prime to D. So when it is co-prime to D, it will map to 1 or -1. Okay, so that is okay, I suppose. So we fix this. So we fix this and want to show, goal is to show L chi of 1 is not equal to 0. So it is a little involved. So L chi of 1 is chi of n by n, sum from n equals 1 through infinity, which is actually so what this proof involves is somewhat analyzing the partial sums. Okay, plus the remaining term. Okay, there is a little bit of noise, so maybe I'll move. Sorry about that. Yeah. So this term is actually we can estimate. So this one in absolute value. So if you look at what can we say about that kind of stuff? Okay, so this is actually you can do it by the partial sums. I mean the summation by parts business that we did before. If you remember how we showed the convergence of L functions for S positive is to do the partial sums, right? Not the product. Where is it? No, it's not here. Where is that? Here, when chi of n, when summation an is bounded, When partial sums are bounded, then summation an by n to the s converges. So what did we do? We took the summation from k to l, and we showed that that is bounded by constant times basically k to the power of s, right? And so all these partial sums are bounded by basically the first term here, k to the 1 by k to the power of s. That's what we got. So from the same analysis, so we see that this is actually big of 1 over capital N. So I will use the notation. So it is bounded by some constant over capital N. Okay. So L chi of 1 can be approximated by these partial sums. So if this is 0, then these partial sums should be approaching 0. So that is something that we are going to use. Now there is a part which is totally unmotivated for me. I think it is Dirichlet's original idea apparently in a different problem. That's what Stein and Shakachi say, that he did not use it in this problem but in a different problem, and it's a very strange thing. I cannot motivate it, but it is so. These words like consider are the tricky parts in mathematics. So those are the ones you don't know how somebody got. So consider, okay, sum over k comma l such that
Sorry, maybe
huh,
it's obvious that the sigma from n plus 1 to infinity chi n by n.
huh.
So that is actually bounded. Oh, is that actually bounded?
Yes. So because this is a non-trivial real character.
Oh, I see. Okay, thank you.
Even if you put 1 by n to the s for some s positive, it will be converging. That's exactly the thing I showed. I will later say a few other things which I will say are similar and do it yourself, but this actually follows from here. What we showed is that sum of k to l, an by n to the s, is bounded by a constant. This m was the bound for the partial sums of a, divided by basically k minus 1 to the s, which is like k to the s. So even if you let L go to infinity, this thing is bounded by that 1 by k to the power s. So here I'm using it with s equal to 1. I'm using that with s equal to 1. N to the s with s equal to 1. Okay. So that's how I get this. So
No, I guess his question was more that partial sums of chi n are bounded. That's what it is, right?
oh, partial sums. Partial sums are oh, is that the question? Whether partial sums of chi are bounded? They are, because chi is periodic. So chi, it sums to 0. If you sum over any consecutive d integers, it sums to 0.
Good point. Thanks, Kaushik. Yeah.
So in fact, that is exactly how we use that other lemma to show that L chi is well defined for S positive. So did I even? Yeah. So this one, if chi is a non-trivial character, then summation chi n is bounded. The reason is any consecutive d things, if you add up, you get 0. So you can just the same things will repeat. So the partial sums are also having period d. So it's a bounded sequence. Okay, so that's so here I just recall proof of convergence of L chi for non-zero infinity. Okay, so now we consider this. So this is the consider part. So here they say you consider this chi of k over square root of k comma L. Okay, don't ask me how they came to this. This may be if there is a conceptual underpinning to this, then I'm absolutely unaware of it. I know, I'll just tell you what I mean, it's just from here. So you consider this chi of KL over square root KL. So it is, what are you summing over? So if you fix K comma, sorry, this I did not complete. This is sum over K and L greater than equal to 1, but KL less than equal to N. That's what we are going to consider. Okay. So k and l will always be greater than equal to 1. I won't write it later, but the product is less than n. So that is a hyperbola, right? So that is a hyperbola. So k, so this is, if this is x, this is y. This is the xy equal to n. So as n moves, this hyperbola will move up. Okay, and you are summing over all lattice points which lie below this. There are finitely many because the smallest is 1. So it is all lattice points which are here. Like this. So we are summing over these lattice points. So you cannot say exactly how many there are. It's a bit tricky problem, that those kind of things. But yeah, so you are summing over all things which lie below the hyperbola. So the whole thing will be to consider this in 2 ways. Okay, so one way is to sum it by the product, which means summing along the hyperbola. So in other words, you fix the product. So let's call it R. R equals 1 up to n. I take all and then sum over k comma l such that kl is equal to R. Okay, chi of k over square root of kl. So you sum along hyperbolas. Okay, so one way is to sum along these hyperbolas. You fix KL product and then sum all the things on that, all the lattice points lying exactly on that, and then sum it. So that will, in this case, KL is R. So you'll get sum over R equals 1 up to n, 1 by square root of R. And then you get the chi of K over what K? Don't write K equals 1 up to R. It is all K which have to divide R. Okay, so K has to divide R. Otherwise, it's not being considered. It has to lie on the lattice. It's not every K up to R. Now, this is something we have to worry about. So what is this product? What is this partial sum of chi? Yeah, we already said it is bounded, but now, in fact, it is actually positive. What we want is a lower bound for this. So we will get a lower bound for this. Okay, so we want a lower bound for that. How will we get a lower bound for that? So the idea is this. So you just take, suppose you take R equal to P1 to the A1 up to some PM to the AM. Let's say it's the prime factorization of R. Then what are the possible K? Are just P1 to the B1 up to PM to the BM with 0 less than equal to BI less than equal to AI. Okay, so these are all the possible divisors that will come in this sum. So, and what will be the chi of that? Chi of K will be chi of P1 to the B1. It's chi is multiplicative, right? Completely multiplicative. So it will be chi of P1 to the B1, chi of PM to the BM. So what is this sum then? That sum over K divides R, fix R, and you divide sum over chi of K. We are analyzing the partial sums a little more carefully because now I don't want to say it is bounded in absolute value. I want to say it's actually non-negative, and I want to say it is often 1 or at least 1. So I want a lower bound for this. So this thing will be sum over all BI less than equal to AI for I equals 1, 2 up to M of this product chi of P1 to the B1 chi of PM to the BM, which factors, right? It is the product over all primes which divide, or just I equals 1 up to M. It is, yeah, let's write J equals 1 up to M. What is it? We have a sum. So chi of P1 to the 0, chi of Pj to the 0, chi of Pj to the 2 or 1 and so on. So 1 plus chi of Pj plus chi of Pj square plus dot dot dot. To the, sorry, not M, it is Aj. That's the product, right? So you get this. So this is what you get. Now you see this one, the key point is it starts with 1, right? All these things, they starts with 1, and all these are +1, -1 are 0. Okay, so chi, these terms are 0 or 1 or -1. And it starts with 1. That's the key point to notice. Starts with 1. So how can this be? So this is necessarily and there will be alternate. If something, if it is minus, if this is, if it is 1, good, it's a big number. It is something like aj plus 1. We don't care. If it's -1, then it will be alternating 1, -1, and so on. So still it can never be negative, right? Because you start with 1. And if it is 0, no problem. All these are 0 and you will get 1. So this whole sum, so this sum is greater than equal to 0 always, and greater than equal to 1 unless, so when can it be actually 0? Okay, when can it be actually 0? Unless chi of pj equal to -1 and aj is even or odd. I want aj even. No, is odd. If aj is odd, the number of terms here is aj plus 1. So 1 minus 1, 1 minus 1, that will cancel. So the only way this can be 0 is that chi of pj is -1 and aj is odd. Otherwise, it's going to be non-negative. So because of that, this is, so what does it mean? So in particular, this sum is Saumendu, right? So sorry, Saumendu, there was only noise. Can you try again? Were you asking something or?
You want, for it to be 0, you want aj to be even, right?
No, the number of terms here is aj plus 1. You are starting at 1 and going aj 0 to aj.
Oh, you are starting at 1. I see.
So the number of terms is aj plus 1. So for you need an even number of terms to cancel. So aj odd is the case that cancels. So what I am saying is that this is greater than equal to 0 for all r and 1 for r a perfect square. If r is some, let us say, t squared. Because aj even, that is aj even for all j, if and only if r is a square. All prime numbers occur with even powers, right? So that is what it is. So this sum, what, going back to that, so I'll is it okay? So from here, I will go back here and write it. So this is greater than equal to, and this whole thing comes from the reasoning below. So I get here sum over r equals 1 up to n, 1 by square root of r, and then here we get only over squares. Let's just sum it over squares. How many squares are there? Which sorry. Sorry. So when r is a square, right? Sorry, I made a mistake. So let's call r as t squared. So then, so I get sum over t less than equal to square root n. T, r is t square. So for any perfect square, this is at least 1. So I'll get 1 by t at up to t less than equal to. Is this okay? For every perfect square, I get this is at least 1 and the rest are non-negative. So I only take sum over for the perfect squares, and that is t going up to square root n and 1 by square root of t square, which is 1 by t. And you know this is very well. This is log square root n plus big O of 1. We know this well, right? So when you sum 1 by t up to a point, you get that it is log of that number plus big O of 1. In fact, the difference converges to a constant, but that's we only need that. This is going like log root n, log n. Okay, so that's all we need. Any questions here? So this is one way of summing this business and getting a lower bound. Now we do it in another way, and we'll try to get a contradiction that L chi of 1 is 0. The way L chi of 1 will enter is as an approximation to this partial sum. Okay, so that's how we will see L chi of 1. But any questions here? So now let's sum the same thing in another way. By the way, this proof is exactly what is given in Stein and Shekachi as well as Apostle. So we'll sum this. So what we need is this chi of k over square root kl, all the sum over lattice points under this hyperbola. So how are we going to sum this? So we are summing over kl product less than equal to n, chi of k over square root of kl. That's what we are interested in. We will do it like this. So we will take, k bigger than, so k is for me, okay, so let's do it like this. So sum over L less than equal to square root n, sum over k less than equal to square root n, chi of k over square root kl. So this is, I am summing over the part which is in this square part. So square root n to square root n. So I am summing over those lattice points first. No, actually is that right? No. Sorry, I want to know. That's not what I want to do. No, 1 second. Just I want to sum over k bigger than square root n actually. So yeah, sorry. Let me just do it properly. So this is for k bigger than square root. Yeah. So okay. So now I understand. So k. So you take any L, and then you sum from k. KL has to be at most n. So k less than equal to n by L. But also let's write it as bigger than square root n. Okay. So maybe one of them I should make a strict inequality. Yeah, so you sum over L first and then K first. So there are two things. So we'll separate K less than square root n and K bigger than square root n. Okay, so these two will be handled separately. So let's handle this one. So here you have something like this. So the inner sum is, let's pull out the 1 by square root L outside, and then you have K equal to square root n to, I mean, of course, you have to take integer parts, that is understood. This means above this and below this, chi of k over square root k. Now again, we can use what we have done before. What about this partial sum? Right? This partial sum we know is bounded by, I mean, this whole thing in absolute value. So let's say the inner sum absolute value is bounded by 1 by square root n, a constant, times, what was it, k to the power s, right? So square root of n, I think. Is that right? So what did I say here? Just a little while ago I quoted that. So the chi of n by n became the first term. Yeah, so it is the first term. But here it is divided by square root k. So let me just go back and see that business here. Yeah, so what we get is the partial sums from k to L will be bounded by the lowest one, 1 by k to the power s. So here s is half. That's what I'm using. So when s is half, so this will be bounded by square root of the starting point, which is square root n. So this is again by the we call the convergence of L chi proof.
I mean, minor point. This first sum, because you are summing k bigger than root n, then it should be L only from 1 to root n, right?
Right. Otherwise, the inner sum is empty. Yeah, you're right. So k also goes only up to square root n. You're right. Actually, k cannot be small. Yeah, that's correct. Yeah, you're right. So, but here I have both. Yeah. So here I have both less than and bigger than. Yes. So you get this. So the total is less than equal to c over n to the 1/4 summation 1 by square root L equals 1 up to square root n. Yeah, now it is good that you pointed that out, because otherwise I would probably get something worse. When you sum 1 by square root n, what do you get? So it's like integrating, right? So integral of 1 by root x is root x. So it is like 1 by n to the 1/4, and then this will be another constant times square root of square root n. So when you integrate 1 by root x, you get root x, and it is something like this. So this whole thing is big O of 1 actually. Okay, so this first sum end is actually big O of 1. So you now look at the second one. So let's look at that one. What is that? So you are summing over. Yeah, we interchange. So you get sum over k going up to k goes from 1 to square root n. Let us say k is only up to 1 to square root n. I pull out the chi of k over square root k out. And then I have the sum L equals. What does L go up to? L goes up to 1 over 1 to n over k, right? And I have 1 by square root of L. Is this okay? I just interchange the sum. So chi of k over root k comes out, and this is summing up to this one. And now I want it a bit more precise actually. So yeah. So let's just write that. So just like, so earlier we used this fact that summation 1 by n. So we use that summation 1 by n is up to capital N is like log n plus big O of 1. So similarly, we will want a precise form of the summation 1 by root k. These things are very easy to do by comparing integration to summation. Even more particularly, if you understand the Euler summation formula, which is the integration by parts like formula which I indicated, these things can be written very precisely. You can get very fine approximations to this. The first term is given by the integral, but you can put finer approximations. So let me write this. L equals 1 up to, let's use some other symbol, 1 by square root L. To the first order, it will be like the integral of 1 by square root x from 1 up to m dx, which will give me 1 by, so 2 times square root of m, right? That is what that will give me. So here you will have 2 times square root of m. But then the next order term is some constant. In fact, the difference will converge to some constant, and then plus big O of, I think, 1 by square root of m. Okay, so this maybe I will leave as exercise. So this is a basic calculus type exercise. You have to compare the sum to the integral. First order is this. The next order gives you a constant. Just like with log, you had the integral gave you the log, right? 1 by k. The integral gives you log. There is a remaining constant term. But here there's an error term that also is 1 by root m. So I will leave that as exercise, because anyway I will now run out of time. So this one we can write as sum over k equals 1 up to square root n chi of k over square root k, and here we are doing up to n over k. So it is 2 times square root of n over k plus a constant plus big O of the reciprocal square root. So square root of k over n. So what does that give me? So that gives me, the first term gives us 2 square root n k equals 1 up to n chi of k over square root k. Okay, so that is okay. The second term will give us c times square root k, and the third one is even yeah, since I got big O, I should write. Yeah, I cannot. Yeah,
First
one should
term
be a bit.
denominator is k, right?
Sorry.
First term denominator is k, right?
Ah, yes, yes, yes. Very, very important. Yeah, this is k. The square root k gives k. So this is right. This is right. So this is k, not square root k. In the second term, it is square root k. Third term, notice that I have written big O, means it is in absolute value bounded. I only have the bound in absolute value. So I cannot use chi and all that. I have to just use the bound of 1 here. So we will just write that as big O of some k equals 1 up to root n. I have to just bound chi by 1. So I get 1 by root k cancels, and I get 1 by square root n. So this whole thing is actually 1 by root n into, so this is big O of 1. Okay. And this one, what is it? It is also big O of 1 because we know it converges, right? It converges to L chi of half. It will just converge to the L function at half. So this is going to be big O of 1. Now this quantity will converge to L chi of 1. Actually, in fact, I want a remainder term. That's very important because it's getting multiplied by something that is big. I should write the remainder term, and that's where I go back to this. Summation chi of n over n is actually up to n is like L chi of 1 plus something that is big O of 1 over n. So here it is L chi of 1 plus something which is big O of, it's summing up to 1 by root n. So it is L chi of 1 plus big O of 1 by square root n. That is, that second term is important now, you will see, because it's getting multiplied by a big term. Getting multiplied by 2 square root n. So these two are big O of 1. So what happens? If L chi of 1 is 0, then this first term is 0, which by the way is 2 square. So this term is 2 square root n L chi of 1 plus big O of 1. So this is big O of 1, this is big O of 1, this is big O of 1. If this was 0, the whole thing would be big O of 1. Then the whole sum is big O of 1 as n goes to infinity. But you already showed by summing over hyperbolas that this is actually lower bounded. You got a lower bound of log, so this is star. That can't happen, right? So this is an upper bound actually. So here, yeah, this is an upper bound actually, sort of. Somewhere I have put absolute values. Yeah. So this is an upper bound. It can't be smaller than the lower bound. So this contradicts star. So L chi of 1 cannot vanish. Okay. That's the proof. Okay, I just finished in the nick of time. Unusual for me and without actually messing things up. Okay. Any questions here? It's a little involved. It's not complicated. The only thing I use repeatedly is that summation by parts formula. In fact, I pretty much, yeah. So that is a very useful thing in analysis, knowing the summation by parts formula. So, okay, so that finishes everything. So I have a couple of minutes. So if there are no questions, then I will just quickly mention what Sir does in JP Sir's book, what he does using a little complex analysis. Okay, so but are there any questions, comments? If that's not necessary to say, I can skip that too. Are there any questions, comments? Okay, if not, then let me just do this. Just mention what happens. So the other way is you take this lemma which we had. This one. The product of L functions is this. So let's just write that. So you are starting with this product over chi. L chi of S is product over P coprime to D 1 over 1 minus P to the S. Sorry, what was that? Sorry. There's no chi anymore. 1 over 1 over P to the S times F of P whole raised to the power G of P. Where Fp was the order of P and Gp is the quotient by phi of D. So we have this. So the point is this, so the right hand side, so this is for S bigger than 1, by the way. That's what we proved for S bigger than 1. But the right hand side, you see, if you expand term factor for P, you get 1 plus, so you get, what is it? Yeah. So let's forget the G of P for the moment. That is a multiple only. So you'll get 1 plus 1 by P to the SF of P plus 1 by P to the 2SF of P plus dot whole raised to the power G of P. So this is actually sum, so you can expand it. So it will be a sum over 1 by P to certain powers with positive, all coefficients positive. Okay, and what he shows is that, okay, so since I'm running out of time, so a small argument shows that right hand side is bounded below by summation 1 by n to the S times. So because see, this will have a P to the S times F of P, G of P term will be there. Okay. So that
it's 1 o'clock.
So it is actually, you can bound it below by sum over n equals 1 through infinity, because you're taking product over primes and there is also this G of P, this will come. So this requires a short argument, but you can bound this below by 1 to the S times phi of D, where phi of D is the quotient function. This comes as product of Fp into Gp, and the rest is similar to earlier. When you take products over this kind of thing over primes, you get all sorts of numbers raised to the power S, right? And Fp Gp will give you the phi of D, which is infinity if S is less than equal to 1 over phi of D. Okay, so this right side diverges when S is, so this identity is valid only for S bigger than 1. Okay, but we are saying that at a point which is 1 over phi of D, this thing diverges. So what? There is no contradiction right away from this, but the point is, if so in fact, one can make this real part of S bigger than 1, and then can argue if L chi of 1 is 0 for some S, for some chi. If one of them has this vanishing, here is where the complex analyticity comes. The whole thing is a product of holomorphic functions, so it is nice. So, and the trivial one has a pole at 1. So if one of them vanishes, then the product function is analytic all the way, is analytic for real part of S positive. Okay, the only singularity is at S equal to 1. If that has been cancelled, then it will become analytic all the way to real part S positive. One more small point is that then it will have to, so then it can't, but the one small point you may say is that, okay, this may extend, but it may not be equal to this. But the thing is, it's like with power series, if a power series converges, if you have an analytic function on a disk, and you take some point in the inside, the power series around that point will converge all the way to the largest radius you can inscribe inside the domain. Similarly, here there is a theorem to the effect that if you have a Dirichlet series, then this will converge all the way to the lowest point where it is analytic. So there is a contradiction. So these two lead to a contradiction. Okay, I don't have time and enough. It's already 1:03, so I will just stop here. So that is the way Serre does it. So he doesn't have to separate into real and complex characters and so on, because you only need to remove the pole at 0, pole at 1. That's what he does. That's what he does. Okay. Okay, so I'll stop recording.